And beyond. This is day 11 of my DSA series. Today I will be discussing a question related to linked list. So let's dive right into the question. So today I will be discussing question number 141. That's linked list cycle. So let's dive right in. So the question states, given the head of a linked list, determine if the linked list has a cycle in it. There is a cycle in a linked list if there is some node in the list that can be reached again by continuously following the next pointer. Internally, position is POS is used to denote the index of the node that the tail's next pointer is connected to. Note that POS is not passed as a parameter. Return true if there is a cycle in the linked list, otherwise return false. So we can look in this example, like from the naked human eye, it's clear that this has a cycle because after go from -4, we have a loop back to 2, and then this is a cycle that we have. So we're just going to return 2, and position is equal to 1. That's basically the index. That is the index of this element. So as it mentioned over here, position is used to denote the index of the node. Index of the node the tail's next pointer is connected to. So tail's next pointer is connected to this. So that's the index. We return true. Over here again we can see there's clearly a cycle. We basically return true over here as well. Position is 0. That's basically the index of this element. Over here there's only one element. There isn't any cycle, so we can return false. And basically constraints are given, so the number of nodes in the list is in the range 0 all the way up to 10 to the power 4. Node dot value goes from -10 to the power 5 all the way up to 10 to the power 5, and position is -1 or a valid index in the linked list. So we don't have to basically deal with position. That is something that they have done. And they also have a follow-up. Can you solve this question using big O of 1 constant memory? So let's dive right in. I'm going to copy this case. So hopefully the question did make sense. We basically have a linked list. We have the head. We have to basically detect whether there is a cycle in the linked list or not. If there is, we can simply return true. And if there is not, we can return false. So this is a linked list that we have. So how do you know there's a cycle? We can see that this is a cycle, right? So what is the brute force approach to solve this question? So we clearly know we could use a data structure to store all the nodes that have been seen thus far. And if that node is seen again while traversing our linked list, that basically means that it does have a cycle. So what did I say? We're going to take a data structure, store the nodes that have been traversed, and if we encounter the same node again, we can simply return true, meaning that a cycle is there. Because if the same node is repeated, that means there is a cycle. And note that I'm saying same node, not same value. For example, there could be another node that has the value 2, but it could be a totally different node. And how could it be a different node? Its next would basically be different, so as to speak. So that is what I'm saying. We're going to store the nodes, and if we find out that this given node has already occurred before, we can simply return true, meaning that the node has occurred. That is all that we have to do. So since we want to track the occurrence of nodes, you can say that we can take a set, and in the set, what are we going to store? We're not going to store value. We're going to store the actual node. So suppose we have a set. Let's call it S. For the time being, we have a set S. So it basically stores all the nodes thus far. So what I'm going to do is I'm going to take a temporary variable or temporarily pointer. It's basically going to be the head. Keep on moving it ahead. So when I move, first what I'm going to do is I'm going to check, is this in the set? If it is, that means our answer is true. If it's not, we continue on. We basically continue on, and if we basically reach the end, there's no worries, we can return false. So for example, T, we first check is 3 in the set. No, it's not. So we can use the dot count method, or we can use the dot find method in C++. So we add it. Basically then what happens is we take this T, we take this T, and we move it ahead. We take the T and we move it ahead. So let's say I'm going to consider this T. I'm going to move it ahead to this element. Is it in the set? No, it's not. Add it, move it ahead. Then we're going to come over here. This is going to be our new T. It's 0 in the set. No, we can add it. Then we come over here. It's -4 in the set. Absolutely not. So we add it. Then we come over here. We encounter the T again, or this is our new T. Encounter 2 again. 2 already is in the set. We can return true, and that is all that we have to do. So this was the approach using sets. So hopefully this approach did make a lot of sense to y'all. So this was simple. You can try to code it up. I'll show the code later. Now what's the second approach? So whenever we are dealing with linked lists, there's a special pattern called fast pointer and slow pointer. And if you don't know what that is it's basically we take 2 pointers. They start at the same position. We move one pointer 1 position at a time, and we move another pointer 2 positions at a time. So effectively what happens is we can say that when one pointer, the fast pointer, when it reaches the end, we can say that the other pointer is always going to be at the middle of the linked list. And what we can conclude from that is once a single list, the slow pointer, once that reaches the end, we know that the other pointer would also reach the end because it's moving at double the rate, right? So just logically think about it. If something's moving at twice your rate, by the time you go from, suppose, point 1 to point 2, what happened? They basically, by the time you basically traverse this, so the fast pointer, it would traverse the entire list. That is what I'm trying to say. It would traverse the entire list. Hopefully that did make sense. If that didn't make sense, I'll basically gonna use our slow pointer and fast pointer to make things clear. So this is our fast pointer, and suppose then we have another pointer. We call that our slow pointer. So what do? We first move the fast pointer 2 positions. So here we go. We take this fast pointer, move it 2 positions. Fast is equal to fast dot next. Copy this entire thing. Fast is equal to fast dot next. Fast is equal to fast dot next. And the slow pointer, it basically moves 1 position. So let's take this slow pointer, it moves 1 position, comes in over here. We check, are both the pointers pointing the same element? They're not. And what's going to happen in a cycle is, like I mentioned, when our slow pointer reaches the end, the other fast pointer would also reach the end. It would just be the case that the fast pointer has basically done 2 traversals because it's going at twice our speed. And that's quite intuitive. Hopefully that did make sense to you, but I'm also going to show the visualization. So this is our first step. Now fast pointer goes to next, and then it goes next dot next. So this next goes all the way back to 2. And our slow pointer, we take our slow pointer, goes 1 position ahead, comes to 0. And after this, our fast pointer basically goes 2 positions ahead again. So 1 position, 2 positions. And this is our slow pointer. Slow pointer goes ahead 1 position, and we see that slow and fast come to the same element, meaning that there is a cycle. So that is the intuition behind it. We're going to have 2 pointers, a slow one and a fast one. Slow moves 1 node at a time, fast moves 2 nodes at a time. And due to the fact that fast is moving at twice the rate at which slow is moving, we know that by the time slow reaches the end, fast is, if there is a cycle, fast is definitely going to catch up after some time, because we can say by the time slow reaches the end, fast will also reach the end. The only thing will be that the fast will basically be able to traverse the entire linked list twice. That is the only difference that is being made. And if fast reaches the end and this is not the case, we can simply return false. So I just wanted to tell you another condition about fast. So till when do we move fast? We basically can move fast till fast is not null. So like in this case, suppose there wasn't this cycle. Suppose there's no cycle over here. Suppose what I'm trying to say is there's no cycle over here. Suppose this was not a cycle. So till when would we move fast? That is the question I asked you. Till when would we move fast? Let's see. We move fast over here, and then fast would reach the end. So if fast is null, that means we can't go further. And if there are odd number of nodes, suppose there's just this 0. So we can stop when fast of next is null, because if fast of next is null, we know that fast of next dot next wouldn't really be anything. That would go out of bounds. So I just wanted to explain that condition to you as well. So hopefully this did make sense. So I'm gonna code it up. So I'm gonna code up the fast pointer approach first. It's way shorter. It doesn't really take a lot of time. So we can take list. We can take list node star. List node star. Slow, it's gonna point ahead. Then we take list node fast. It's also gonna point ahead initially. And like I mentioned, when do we move out, fast is not equal to null. And we have to use an AND condition because both of these should be true. Fast is not equal to null, fast of next not equal to null. Because if fast was null and we use the OR, fast dot next would be null, so this wouldn't really work. Or if fast was null, this wouldn't really make sense, so we have to have an AND statement. So what are we going to do? So we check fast and slow later on, because fast and slow start at the same position. If we check them up initially in our while loop, it wouldn't make sense. It's always going to return true, and that is not what we want. So what we're going to do is simple. We're going to go slow is equal to slow of next, and fast is equal to fast of next of next. That is what we're going to do, fast of next, and then we're going to check if slow is equal to fast. They both point to the same thing. We can return true, and in the other case we can simply return false. And this is all that we have to do. We return true if both of them are equal. If both of them are not equal, no worries from our end. We can simply return false. And as you can see, we've got the correct answer, and it's not taking too much time. So like you can say it's big O of 1, and we're not taking constant. We're taking constant space and big O of 1 because we're traversing through the linked list at max. Like we can say we're traversing technically 2 times, but that converts to big open anyways. So this was our first approach. And do you want me to show the brute force approach? Okay, so let's go ahead with the brute force approach. We're going to take an unordered set, and like I mentioned, we're going to store nodes in it, so we have to do something like this: list node star unordered set. Let's call it S. And what can we do? We can directly move head, like that's not an issue. So we can say that while head is not equal to null. What can we do? First we check if there's some indentation error, so sorry. First we check while head is not null. That is simply what we have to do. We don't care too much. While head is not equal to null. While head is not equal to null. What do? We check if stock count head. If it is there, then we can return true. Stock count head means head is already present. That's what we're trying to do. Find, or we can do stock count. And then on the other, we're just going to do dot insert. What are we supposed to insert? We can say we can insert head. We're inserting the node. Head is equal to head of next. And if we don't get a true value, we can simply return false, meaning that no cycle has been detected. So let's run this approach. The time complexity is the same. The only problem is that we're taking a extra data structure, and you don't really want to do that for this case. So this was the second approach, where we took an unordered set. We use the dot count method, and then we get the required answer. So these were the two approaches, and you can see runtime's not that good. So hopefully you enjoyed this video. Please feel free to comment what my next video should be about, and let me know if my videos are actually helping or not. So thank you so much for tuning in. Au revoir.